Welcome back. We are in momentum here on worksheet 2, and here's problem number 1. So a 12,500 kilogram railroad car is rolling along some level track with a speed of 4.5 meters per second, collides with a secondary stationary, so at rest, car with a mass of 24,700 kilograms, so roughly twice as big, twice as massive, I should say. Two cars lock together. Okay, so if they lock together, they're going to be moving together after the collision. And as always, we identify our action there, and that is some collision. And we're going to make a picture here, 2 pictures, both before and after this action here. So we got one railroad car right here. You're drawing it with me. And this guy, we'll call him railroad car A, maybe. And he'll have the mass of A will be 12,500. And he's rolling along going that way, let's say, with a velocity VA naught of 4.5 meters per second. And he collides with a one that's like twice as massive, so I'll just go ahead and draw it about twice as long there for descriptive sake. And the mass of that one is 24,700 kilograms. And this guy, oh gosh, that's VB, naught is 0. Two cars lock together. Here's the ground here. Oh, that second wheel is popping a wheelie on B, even though he's not moving. So now they lock together afterwards. So here's car A. And then there's like some sort of clasping mechanism. Here's B. Add that clasping mechanism onto each one of these guys. Right. So now these guys are going to be moving along. I kind of think about it and go, A runs into B. Okay, they're both going to be going, this direction. So this will be like the velocity of A and B. And we don't know what that velocity is. Cool. So determine, A says determine the final speed of the two cars after the collision, and B says determine the change in kinetic energy of the system. Where's the kinetic energy go? All right, well, first we kind of define our system here. And as always, our system can be whatever we want. I'm going to make both car A and B my system. And so now if I made everything that's interacting here, everything that is moving and transferring motion or momentum between each other, then I know that the change in momentum of my entire system, and therefore universe, must be 0, so the momentum beforehand must be equal to the momentum afterwards. And what is the momentum beforehand? Well, the momentum beforehand is just the momentum of A plus the momentum of B, and that's going to be equal to the momentum of, well, it's going to be, you can write it in a couple different ways. You can write it the momentum of A plus the momentum of B, but you could also say, hey, I know that A and B are moving together. Let me show you some mathematical tricks here of how you can write it a little bit differently. So we first, let's put in some values we know here. We know the velocity of this guy is 0, so it's going to have 0 momentum at the beginning. If I go and put this in, this is the mass of A times the velocity of A at the beginning. This will be the mass of A times the velocity of A, and that's at the end. And this is the mass of B times the velocity of B at the end. Now, because they're moving together, we know that the velocity of car A has got to equal the velocity of car B. Well, if I know that, then I can go ahead and put that in. And when I do that, check this out. I have the mass of A times the velocity of A plus the mass of B times the velocity of A using our blue equation there. Well, hey, can I factor anything out here? Oh, yeah, I can factor the velocity of A there out, so now I just have the mass of A plus the mass of B and times its velocity. Well, hey, that's like the exact same as if instead on the right hand side, if instead I said something, let me write it a little bit further over. If instead I said something like this, what if on the right hand side, instead of saying the momentum of A plus momentum of B, what if I realized that they're going to be moving together, so it's the momentum of AB? Now, if I did that, I would say, oh, it's the momentum of A plus the mass of A plus the mass of B, and that's times the velocity of like AB. Well, the velocity of A and B together, is going to be either the velocity of just A or the velocity of just B. Now notice this green statement right here is the exact same as what we've written over here. Okay, cool. So you can kind of think about it in any different way. And even if you think about it as two different things, it mathematically comes out to be the exact same as if you thought about it as two combined things there. Okay, cool. All right, so moving on, no matter which way you think about it, it comes out to be the exact same thing in the end there. So now let's think about what we know. We know the masses of A and B here. We know the velocity of A at the beginning, and we just don't know the velocity of A at the end. So we only have one variable here. So let's go and let's solve. You grab your calculator. I'm grabbing my calculator too, and looking at these known values here. You get 56,250 for the left-hand side there. And I'm going to take that and I'm going to divide it by the mass of A plus the mass of B that we have there. And we find that it's 1.512 meters per second. I used only standard international units, SI units, so I know that it's going to be meters per second. Oh, and I looked down here at the key. It says 1.5. That's nice. Now it also asks for determine the change in kinetic energy of the system. Where's the kinetic energy go? Well, let's go do that. Kind of ran out of room vertically here, so I guess I'll have to squeeze that in. I'm going to do that over here. So let's find the change. Maybe I'll erase this line a little bit. Okay, that's a little bit better. All right, so now we're going to do the change in kinetic energy. Sorry about the order here. Change in kinetic energy, well, let's write it like this. It's the kinetic energy at the beginning is equal, well, we're going to figure out what the kinetic energy at the beginning is, and we know at the beginning it's going to be the kinetic energy of A at the beginning plus the kinetic energy of B at the beginning, and we're going to compare that, and I guess we'll put like a question mark. Is it going to be equal to, greater than, less than? Sounds like it's not going to be equal to in the question here of the kinetic energy at the end plus the kinetic energy at the end of both these objects. Now, knowing the kinetic energy formula is 1/2 mv squared, we know that this guy right away is going to be 0 because it's got 0 velocity there. So if I go and do that, that's 1/2 ma va naught squared. And this guy over here is just going to be 1/2. Well, they're going to have the same velocity here. So I can think about it as the mass of A plus the mass of B times the velocity of A, B, or whatever, however you want to say that. But don't forget to square that as well. And so then we'll compare those. So we grab our calculators one more time. And 0.5 times 12,500 times 4.5 squared. And on the left-hand side, we get 12,6562. I'm sorry, that's 126,562.5 joules, capital J joules. That's for the first bit. And the second bit is and the second bit is 42,000, sorry, 527.72176 joules. So we see that we definitely decrease here. So we have a greater amount at the beginning here, and it decreases. And I believe it asks how much it decreases by, determine the change in kinetic energy. So the change in kinetic energy is always going to be the ending minus the beginning. And I'm kind of running out of room here, so the change in kinetic energy is going to be the ending minus the beginning there. So my ending bit minus the 126,562.5, and I get negative 84,034 we'll just say 78 joules. And so our kinetic energy decreases by that amount. Interesting. Now, does energy get created or destroyed? Hopefully you're going, well, no, we've proven without a doubt that kinetic energy can't be created or destroyed. And momentum can't be created or destroyed. And we've seen that momentum hasn't been created or destroyed. But it seems like, on first glance, that maybe kinetic energy got destroyed. But if I go and I do an LOL diagram for something like this, I'd go, oh yeah, kinetic energy may be transferred from A to B. A lost some kinetic energy, B gained some kinetic energy. But we have a collision here. And what usually happens when we have a collision? Oh yeah, things are like heating up and such. Right. So this is just the change in kinetic energy only. So yeah, maybe kinetic energy does go down by 84,000, but maybe something else, some other type of energy goes up. Oh, maybe thermal energy goes up by 84,304, 84,034 joules. Maybe, that's a possibility. Where else might that energy go? If you kind of think broadly there, what else is getting energy? You might say, well, wouldn't this make like a big sound? Isn't there energy in the sound? Yeah, there's a small amount. In proportion to how much energy kinetic energy A has at the beginning, the amount of energy in that sound is relatively small, and we usually ignore that. But let's think about some others. Where else might that energy go? Where else might there be energy trapped up in? Well, if you're standing next to this thing and you closed your eyes and you had big headphones on so you couldn't hear it, would you still be able to tell that things ran into each other? Yeah. I mean, the ground shakes when trains like run into each other. That's molecules that are like moving around there. And those things then must have energy then. And they do. And so there's like vibrations in the ground there. And there's energy trapped up in that. How much energy in comparison to this? I actually don't know. I suspect that it is a generally small proportion for the total amount of kinetic energy of A, but it's definitely way more than that of the energy that's in the air there for the sound. Like we said, definitely things would be heating up in there as well. So the kinetic energy decreased, but there are plenty of other forms of energy that energy might have gotten transformed into. Notice that's one reason why momentum's a ton easier is there's no forms of momentum. It's just motion. That's it. So it's a lot easier to solve any collision problems using momentum. But the kinetic energy ones are, important as well because it helps us figure out what's going on with the energy. I'd also like to take this moment to talk about the change in energy and the different types of collisions here. So we can see that we do have a change in kinetic energy here. And when we have some sort of change in kinetic energy here, we know that the collision here is somewhat inelastic. Now, the amount of kinetic energy lost there tells us how elastic versus inelastic it is. And we know that this is actually some sort of like continuum. It's not just one or the other, but instead there's like all of these bits that you can be along the way between inelastic and elastic. And what does it mean to be inelastic? Well, that would mean that there's you might say, total loss in kinetic energy when you're completely inelastic, meaning that if something was moving along there, that thing could totally stop and not make the other thing move at all. Well, that's kind of an overstatement there because we know that if there is one thing moving and it runs into another thing moving, there will be some sort of kinetic energy. There will be some sort of movement in the other things, so therefore kinetic energy with that. But it is taking that to the extreme there of losing as much kinetic energy as possible. And then the opposite of that would be elastic, where all of kinetic energy is conserved there, meaning that the kinetic energy doesn't change of the entire system, of everything that's, that's interacting there, I should say. So in this case, if kinetic energy had stayed the same here, then this collision here would be totally elastic. Now, not all of the kinetic energy was lost here. In fact, it was what about 2/3 of it was lost, meaning that maybe it's a little bit closer to the inelastic than the elastic on that spectrum there. Cool, great. Have a beautiful day. See you.